Hello, welcome to ISAT 211, Issues in Modern Production Systems, and this is lecture 8, Quality Management. All right, so we already talked a little bit about quality in our prior lecture, but today we're going to get into a little bit more details. And first, just a little bit recap of what is quality. So the quality, by definition from American Society for Quality, it is the totality of features and the characteristics of a product or service that bear on its ability to satisfy given needs. So here, pay a little bit of attention to both this product and the service. So when we talk about quality, it's actually not just about those tangible physical product we see in our lives, but also the service they provide. For example, in a restaurant, in a bank, in healthcare, it all have quality issues, and then also the quality need to be managed. So if you look at the quality in different operations, we of course talk a little bit, actually a lot about manufacturing products, right? Aesthetics, the functionality, and a bunch of other things related to the product itself. And you all can imagine how is that related to your use of the product. And also if it is in healthcare, there are also kind of quality issues. The quality can be the efficiency of providing the service. It can be, for example, the accuracy, and also if it is can provide the service on time, right? These are all different aspects of quality. So I suggest you to watch this video because of the copyright issues. I cannot play it here in this video, but I suggest you open the link from the slides and watch this video. And same with logistics, especially related to supply chain management. There are also a lot of quality issues, maybe from suppliers. So if you are a supplier manager, supply chain manager, and you get raw materials from different suppliers, then you have to think about, okay, how can I manage the quality coming from the different suppliers, and how do I maintain the same high quality for our production company. And also lots of other services related to the banks or some other settings. I suggest you watch this video and see how the quality actually are managed in both products and also services. So we talk about a product and service, or good and service. There's kind of a similarity, and also there are differences between the good and the service. So please watch this video as well, and you will have a better idea about what's the difference and also the common characteristics. And in general, service quality has 5 dimensions. So they are tangibility, reliability, responsiveness, assurance, and the empathy. So tangibility. So in products, we can physically see that's a product, we can use it, and it's very clear. But service sometimes is not very tangible. However, as a service provider, you can actually make those kind of services more tangible. For example, by improving aesthetics of the service you provide, and also you can let customers to feel that all their needs can be quickly satisfied or met based on the service you provide them. And once you hear or listen, the brand of the company, what they provide, right? For example, when you hear Amazon, when you hear Apple, when you hear about Samsung, you all have an image about the company and other products. So that's how they make those services more tangible. And a second one is reliability. So reliability means they have the ability to complete the services provided on time, consistently, and also error-free, right? And And so in this video, it actually has different scenarios that shows how how the service quality actually failed or not providing high quality of the service. And you can check this video and see how this service quality is important to the company. Well, third dimension is of the service quality is the responsiveness. So responsiveness means it's providing attention and also promptness in dealing with customers' requests, questions, complaints, and problems. So basically, when customers have those kind of issues, you can react fast. And assurance means to inspire trust and confidence with your customers. Right? And last one is empathy. So empathy means to show the customers that you care about them, right? So by providing caring individualized attention to the customers and satisfy their need. And so these are the service quality. And if you are, in the future, you work in a service setting, say a bank or a government agency or healthcare departments, then you can think about, how can you improve the quality of service in those 5 dimensions. All right, we're talking about service quality. Now let's look at product quality. So product quality typically includes 2 aspects. One is the product features. So product features, basically that's the more of a design. Oops, that's more of a design. And if there's no design problem, right? So it means the product features are good. Otherwise, there will be some kind of a design issue. For example, in this one, we can see, here, if we provide more spokes, will mitigate the risk, right? Then the risk of hurting people. Sometimes the kids or people might, put their finger into the fan and then get hurt. Well, if designed this way, you will see it actually solve this issue. So this is more of a design problem, design defect. Well, another type of defect is freedom from deficiencies. So from deficiencies means there's no design problem. The problem is the product you made actually have big variations, and some of the parts actually have a big deviation from the standard, right? So this in this way we call it the freedom from deficiencies. Right? It means more of a manufacturing defect. It's not a design department's problem. It's more a manufacturing department's problem, taking responsibility. Okay, so this is the 2 aspects of the quality in a product. And there is a close relationship between cost and quality. And here in this video, there are, several examples related to the cost of quality. I suggest you also watch this, pause this video and watch this, open this link and watch this video, and then continue this lecture. So basically, if there is poor quality, and it might cause a lot of cost by dealing with the quality failures. And also, if a department wants to improve the quality and avoid those huge costs from quality failures, the company usually also have to put some of the preventive costs into it. For example, training of the employees to control quality, all of those, maybe purchase some of the equipment. These all can be counted as preventive costs, and these are all costs of quality, right? And now let's the quality. We know that is not always right. everything gonna exactly the same, 100% the same. That's typically will not happen. And usually there are variations, and varies can be very, very common. And first, what kind of variations there are. So one is, for example, in this chart, we have operator 1, operator 2, operator 3, and they all perform to the 3 steps, right? Maybe the step 1 is very standardized. Step 3, it also standardized, and then, but for step operator 2, the way that operator 2 operates step 2 is different with operator 1. So in this case, it will actually cause a little bit of variation in the product or service quality. Well, it's the same thing if operator 3 operates step 3, conducts step 3 in a different way. Even though step 1 and 2 are the same as operator 1, it still will also create some kind of variation in the final product and service quality. So this is how it actually comes about with these are the process variations. And if we look at the chart, we will see that for example, if you are looking at a dimension of the product, then or feature, then you will see that the more samples here. These are all the different samples 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these are the dimensions, right? These are the dimensions. And you will see all these dimensions are actually around in a common center here, right? Maybe they're around a common center, and it's all around this range, right? We call it. So it won't be all, all the values are on this horizontal line. Instead, it's all, up and down a little bit. So this is called a variation. If we show it this way. And we know there are variations and they are common, but what causes those variations in the processes? So one cause will be the technology. So technology, for example, maybe you are making one little plastic product. Well, making the plastic little product actually can be made 2 different ways. One is injection molding, another way maybe 3D printing, right? And well, the injection molding and 3D printing are 2 different technologies. Then the product you make, you will see how different they are, right? And for example, if 3D printing, you will see the layer by layer shapes of the product. Well, injection molding, you may see it is created as a whole part. However, there might be some inner either deficiencies in or a little bit gaps in the product in the part itself. And also, we mentioned about different people can providing the same service or operating the same machine. It can be or conducting the same operation. It can be a little bit different as well. So that will also create variations. Okay, so that's why we develop this standardized operation procedure, right? So SOP will help us reduce those variations, because each step is very standardized, designed. So regardless who's going to operate this, machine, or who will conduct this operation, they will just follow the exact step by step, and this is how we reduce those variations. And also people can operate those in different methods, and they'll create a variation as well. In environment, if it is service, it can also be different depending on the environment. For example, maybe you are at a live show, right? And then a lot of audience. Sometimes the actors, emotions or actors' passions might be affected by the audience itself. right? So that's why, one day the audience may be very passionate, while the other, day the audience may be a little bit not that kind of passionate. Then sometimes the actors' feelings can be a little bit different. The way they providing the show also may be a little bit different. So that's about service. Well, environment, if it is in a product, sometimes the temperature, the humidity, or some other settings of the environment can also affect the product itself. And what types of the variations in production? So one type of the variation is a random variation. So random variation means the variation is built in the process itself. And there's nothing wrong with the process. And the process is stable and is predictable. And are still random variations. So in this case, as long as all the data sets, right, all the results are within a range, acceptable range, then we call it the process is in statistical control. So the process is in statistical control means the values of the quality or the different features of the quality actually falling within acceptable range. So that's statistical control. Well, other than the random variations, and also some kind of special cause variations. So the special cause variations is not part of the process, it can be some kind of special event happen or some other factors intervened and then cause the process to change, and then you will figure out the products that you make, the quality of those values of the feature of the quality actually is different, with the standard, or is off the acceptable range. So in this case, we call it some kind of special cause variations. And in order for us to solve this issue, and we just need to find out, okay, what kind of factor actually causes the problem, and then we solve it. And those can be avoided, right? Well, the random ones cannot be avoided. Right? If you want to change those random variations, then you probably want to think about changing a whole process itself, right? And if it is a special cause, then we say a problem. Then we say the process is actually no longer in statistical control, right? Because you'll see some or all, or see even a trend of the values of the data sets actually is out of control, not within the acceptable range. So these are two different types of variations. When you're dealing with quality problems, you need to first figure out what type of variation they are. Now let's look at what is statistical control. Statistical control means we're using actually data to track the attributes values, and all the values within the acceptable range with the upper control limit. With the upper control limit, lower control limit, and also a center. And so here are the attributes. And then here on x-axis, these are the sample numbers from 1, 2, 3, 4, 5, to these sample numbers. And you'll see, all these data points actually varies around a certain center. So this means that these are random variations. As long as they are within the upper control limit and the lower control limit, means they are the values inside this range are all good, acceptable. So we call the processes in statistical control. If we look at from the normal distribution perspective, you will see the left chart here, and under the curve here, these are the probability. So from left to all the way to the right, added up all together, it should be 1, right? So this is a normal distribution. And in this case, what happens is the average or mean here is 1.250, which means that most of the values are actually around this age, right? Around this range, right? And then when it goes to two extremes, then the number of these values are going to low. So this is using a normal distribution to describe the process, 2 different ways to describe the process. And we just look at the control charts. Now let's look at what specific components we have for when we're developing control charts, because control charts are a very important tool in statistical control and also in quality control. And if you are a quality manager or production manager, or even service continuous improvement department manager, and you need to know how to use the statistical control how to draw control charts, and also how to use control charts to tell if your process have quality problems or not. All right. So what are the elements of control charts? First, we need to have an upper control limit and also lower control limit. So these are the limits, right? These are limits that for this process. And if there are some data points that is outside the limit, means they are not acceptable. If they are within, means those kind of data points are acceptable. Right, so two control limits and also data points. So these are data points, and that is for samples, right? 1, 2, 3, 4, 5 into all the samples you have here. And also you need to have a center. Center means this is the mean or the average of the samples you have, sample data points you have here. And also sample number and also the attribute. So this is the attribute. It can be dimension. It can be some other features of the quality. So these are the basic elements of control charts. And now let's look at some of the terms related to control charts. First is the population. So population means these are all the data we have in our analysis. For example, right? For example, a farm is actually a farm is growing a lot of apple trees, right? Growing a lot of trees, and maybe have 100 or 1,000, let's say 1,000 apple trees. Well, within those 1,000 apple trees, say these are different apple trees, right? Different tree within all these apple trees, and they will grow apples, and all these apples are actually different, right? So there may be thousands of apples, right? Thousands of apples here in our farm. But I cannot measure each apple's dimension. So if I want to sell to some some market, then I want to see, okay, I just want to pick the apple apple size to be a certain dimension. Otherwise, I'm not going to use them. Now I want to measure, okay, what is the average apples size in our farm? So in this case, what do we do? What do we do? First, I'm going to look at, okay, all these apples in our farm is called a population. It's called our population. All of those, right? Not excluding one. Every apple in our farm is called a population. So we include everything. Excuse me. Well, a sample means we select, right? We select some apples. We select some apples. For example, if we are looking at maybe select some of those apples, this will maybe call it sample 1. And some of the apples here, sample 2. Some of the apple here, sample 3, or well, some other samples. If we do this, then we call it, each of those are each sample, and in each sample, how many apples in maybe in sample one, there are, say, sample one, maybe we have 10 apples, right? Well, sample two, maybe we have say 5 apples. Sample three, maybe we have 20, maybe we have 20 apples. Well, those 10, 5, 20, what is they are? They are called sample size, right? Sample size. And 1, 2, 3, these are the samples. And 10, 5, 20, these are the sample size. So the sample size for the sample one will be 10. Sample size for sample two will be 5. Sample size for sample three will be 20. So this is the, you know, understand the difference between that. It's a sample size. And most commonly, what we have here is that for all these samples, they are actually the same sample size to be consistent in analysis, right? For example, if I choose 3 samples or more, then for sample one, I'll choose 10 apples. Then for sample two, I also choose 10 apples. And sample three, I'll also choose 10 apples. So this, in this case, in this statistical analysis, and the sample size I have here is 10. And how many samples I have? Here, in this case, I only have 3 samples, right? Then sample size will be 10. So this is you need to understand the difference between population, sample, and also sample size. Okay. Well, let's look at the normal distribution. Well, in the normal distribution, we also need to understand the difference, you know, the average, mean, standard deviation, and also z-value. And a lot of time when I say, you know, people use it, you know, average and mean interchangeably, and what does it mean? Why they can interchange, exchange or interchange average and mean is the same. So average and mean is the same only when the probability for each data point is the same. What does it mean, right? The probability for each data point is the same. For example, say say there are several different sample points, right? Say point one, the value is 10, right? Well, so point two, the value is 5. So point three, the value is 20. Okay. Well, in this case, if you want to calculate the average, right, we just use 10 plus 5 plus 20, right, divided by 3, right? So this is the average. This is the average. Okay. All right. Now let's look at the 1, 2, 3 here. Okay. If we say the probability for this one, right, value is actually 0.3. The probability for the number 2 is 0.2, and the probability for number 3 is 0.5. In this case, when we are calculating, we are not calculating average, we are calculating the mean. The mean will equal to what? It will be 10 times 0.3, right? This is the probability, right? This is the value. This is the value. This is the value. So if the then we use probability times the value plus 0.2 times 5 plus 0.5 times 20, right? Divided by what? Divided by 1. Why is divided by 1? Because all of those actually add up is 1. In this case, you just use a probability. Don't have to, you know, to write it here. You can just write the probability times value. In fact, it's actually divided by 1. It's the same. Then you can calculate what is the value here. So this will be 3 plus 1 plus 1. It's actually 5. You'll see this value is different, right? So this is 30 by 35. 35 divided by 3. It's 11 point something, right? Oh, this is actually this is 20. This is 20. 20. This will be 10. This is actually 14. I'm sorry, this is 14. This is 11 something. So you'll see the average and mean is actually different when what? When the probability for these 3 atoms are not the same. When they are not the same. But if they are the same, we can just use the average, right? We can use the average divided by 3 because each one, if they're the same, well, what is the probability here? Probability will be 1 divided by 3, right? There'll be 1 divided by 3, and this will be 1 divided by 3 if they are all the same. And then when you calculate the mean, it will be equal to 10 times this probability, 1 divided by 3, 5 times the probability, and 20 times the probability, right? It's same as this average. So this is why sometimes we use average or mean, and you need to understand the difference between the two terms and also when they can be used interchangeably. Okay. All right. And next, when we talk about the standard deviation actually means how much variation of the data points in the data set you analyze, right? So that's the standard deviation. And for the standard deviation calculation, we have here is right we use each data, right? For example, we have x1, 2, 3, 4, 5, 7, and then we use x1 minus the average, right? Squared plus x2 minus the average squared, and plus all the way to the end, xn minus average squared, right? Squared. And divided by, remember, if we are using the population, then if we are calculating the populations, and all these data points are what? All these data points are a sample of the population, right? We know the sample, we are looking for the population, then we need to use n minus 1. But if we have all these sample data points and we are looking at the samples standard deviation, then we just need to have it divided by n, because there's no difference. Say if we are only calculating the samples, right? We have the sample data points, and we are calculating the samples standard deviation, then divided by n. If we have the samples data points and we're looking for the population's standard deviation, then we need to divide it by n minus 1, because this is more of a prediction or estimation, right? For rough estimation of a different size. So that's why we use n minus 1 as a correction for that. Okay, so all right, so this is how you calculate the standard deviation. And the next one is the z-value. So the z-value means, right, how many standard deviations it actually move out from the mean, right? Z-value, how many standard deviations move out from mean. When you look at this, normal distribution, right? So this is the mean, right? This is the mean value. And you will see all these data points, right? So for example, if you, they represent what? They represent the value you measured, okay? They represent the value you measured. For example, if it is dimension, right? Maybe say the dimension is 1 inch, then maybe this is the 1 point something inch, right? This is 1 point something inch, right? So these are dimensions. And here, we use how many standard deviations to show it here. right? It can be 0.1 standard deviation and 0.2 standard deviation, can be 0.01 standard deviation, or can be 0.001 standard deviation, right? All those. But these points can be expressed as mean plus or minus some standard deviations. And that kind of value is actually z value. So the z value can be both positive and negative, right? It can be positive and negative, or it can be 0. If it is 0, then that's the mean, right? It can be then mu, plus or minus, right? Z times sigma, right? Because z is 0, then you just have the mu here, right? Have the standard, have the mean here. So this is how you look at this, understand the normal distribution. Now let's look at a normal distribution table, because eventually when during the calculations you will need to know how to use this standard deviation, normal distribution table. All right. So we'll see here that so these are actually z values, right? So these are the z value. We will see the z will be 0.00, 0.01, 0.2, 0.3, 0.4 here until 3. And also here, this is the first digit, right? It's the first digit after the point. And here are the second digit, right? 0.0304. So now let's look at, okay, can you find the z value for probability of 0.9744? Now 0.9744, where is 0.94744? 0.974, okay, here, 9744, we have it here, right? So if we find here, we look for the first digit, right, is 1.9. The second digit is 0.05. So in this case, will be what? 1.95, right? So will be 1.95, right? For this value. So this is a z value for the probability of 0.9744. Well, what does it mean on a normal distribution table? A normal distribution table means, okay, if we are looking at, right, a normal distribution that is 0.97544. So means we are looking for this value. We're looking for this value or dimension or some kind of other things, right? So this is the mean. This is the mean, and we are looking for this value. This will be mean plus z sigma, right? This sigma, and we are looking for here. And the probability all the way, right, from the left to right to this end here is actually 0.9744. In this case, we just need to find this, 0.944, the z value corresponding to 0.9744. Right? Then we know this z is 1.95. Right? This z is 1.95. Then if we know the normal distribution and we know the standard deviation, we can actually calculate what is this point, right? All right. Similarly, on the other way, if I give you the z value, can you find the probability, right? So for example, here, a z value is 2.13. Now let's look at 2.13. We know 2.1. Okay, 2.1 is here, right? 2.1 is here. And then 0.3 is here. We just need to find this value. The probability is actually 0.9834. 0.9834. All right. So which means what? Which means that if there is a normal distribution and you say you have the mean, and there is a z value here, right? Plus z sigma, and the z value here, Z value. You want to find out, okay, you want to find out what? You want to find out what about, what is this probability until here, right? What is this the probability? What is this probability? And then it will actually give you 0.9834. So this is how you use normal distribution table to solve problems, okay? All right, now let's look at the two charts for two typical charts for statistical control. And you know, one is the X bar chart, the other one is R chart. So X bar chart means this is the process mean. We're calculating the process mean over time. And X bar chart means, the R chart means it's a range of each sample, right? Range of each sample. So how do we describe this? For example, same, you know, the apple, right? Say we select several, say four samples. Say sample A, right? Sample A, we select maybe 5 apples. Set 5 apples, right? Sample B, 5 apples. Sample C, 5 apples. Sample D, 5 apples. All right. Then X bar chart means, okay, we're gonna calculate, say, you know, we want to find the dimensions, you know, average dimension of those. So X bar chart, we will find, okay, S1 X bar. So means we measure each apple's dimension. Let's say the diameter, right? We measure each apple's dimension, and then we got a average or X1 bar, okay? Similarly, we can calculate the X2 bar. So this is we calculate the average of these apples, right? These apples average dimension. And this is samples C's, and this is the sample D's, right? So these are the samples. Sample A, B, C, D. And here, we know these are samples. What about sample size, right? Because in each sample, there are 5 apples. So the sample size equals to 5, right? Sample size 5. All right, we know how to calculate X bar chart. Then, you know, after we calculate those, you know, X bars, then you can actually draw these, you know, 5 points here, and then maybe find a chart, right? So this is how you calculate the X bars. Then what about R chart? So the R chart here is R1 equals to what? R1 equals to the biggest dimension of these apples minus the smallest dimension. So basically it's called a range, right? Biggest dimension minus smallest dimension within these 5 apples, right? Within the sample itself, right? This is R1. Then R2, the same thing. Then you can do R3 and R4. R2 will be these the range, the biggest dimension minus small dimension, the smallest dimension in this, you know, among these 5 apples. R3, biggest dimension minus the smallest dimension among these 5 apples. Same thing for this one. Then you can calculate all these ranges and then draw another chart. 1, 2, 3, 4, maybe 5. Sorry, 4 data points. 4 data points, not 5 data points here. Same here. It's actually 4 data points. So 4 data points, right? 4 data points, and then you this is how you get all these data points for X bar and R charts. Well, after we calculate, we find out those data points, we also need to find out the control limits, right? The upper control limit and the lower control limit. And there is a rule here to how to calculate the upper control limit and lower control limit for those control charts. And the rule is when you are calculating the upper control limit, it actually equals to the X bar, so this is the grand mean, right? Plus A2 times R bar, so which is R average. And what does it mean? So X bar, the grand mean is because we already have these means, right? These are the means for each, right? For each sample, right? This sample A. And X2 bars equals to X1 bar plus X2 bar plus X3 bar plus X4 bar, right? Divided by 4, right? So this is how we calculate X grand mean. Well, what about R bar? So R bar equals to R1 plus R2 plus R3 plus R4 divided by 4, right? So this is how we calculate the R bar. And we know the X grand mean and also R bar. And then we need to find out the A2. So A2, we can get this value from a table, right? So from table, this table is already provided to you. If in the homework assignments or in the future, your job is you can just use this A2 value. How do we find out this A2 value? A2 value is related to the sample size, right? Remember, sample size is not about how many samples, it's about sample size. In each sample, how many parts or how many observations you have, right? So all right, so for example, in this case, in each sample we have 5 items, right? So this is sample size will be 5. Then we look at 4, 5 here, right? Is 0.58. So then A2 in that case will be 4.58. So this is how you locate, the A2 value. Similarly, when we are calculating, the lower control limit, we just use X grand mean by minus A2 times R bar. Well, if we are calculating the R chart, then we just need to find out D3 and D4. So D3 and D4 is similar to the A2. You can actually find the factor value from a table, and the value already provided to you as long as you know the sample size. In this case, you'll see the D3 will be 0 and the D4 will be 2.11 if it's the sample size of 5, right? So this is how you find out upper control limit, lower control limit for X bar chart and also the R chart. All right, now let's look at one example here. So example here is, so there are 8 samples, right? We already talked about, okay, there are 8 samples and the sample size is 4. We already know the sample size now here. Its sample size is 4, have been collected from manufacturing process that is in statistical control, right? And the dimension of interest has been measured for each part. It is desired to determine the value of the center, right? Value of the center, lower control limit and upper control limit for X bar and R charts. The calculated value units are given in centimeters for the 8 samples R, right? So here means average values is already given to you. Remember, right? When I talk about, all these samples A, B, C, D, E, F, G, right? H, right? 8 samples. And we say, okay, for each sample, there are, say, the sample size is 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Same of these, 1, 2, 3, 4, 1, 2, 3, 4. And just now we have to, calculate or measure each parts, right, within each part's dimensions or, the values within each sample. But here, it is already given to you, right? The X bar is already given to you. It's this is the 2.008. This is the 1.998. This is the 1.993. Now we do not have to calculate each one of those. It's already given to us. Similarly, the R value is also given to us, right? R value is also given to us. R value for first one is 0.027, and one is 0.011. You can get all those. So it actually made it a lot easier for us, and all we need to do is to find out, what is X grand mean, A2, D3, and D4, as well as R bar, right? X grand mean, we just need to calculate the average of all these X bar values, right? And R bar just calculate all these averages of these values, right? Or the average of these values. And A2, right, is in this table, which you need to find out, okay, what is the sample size? Here, the sample size already saying it's 4. Now we just come here and then find out the A2 value, D3 value, D4 value. Then we can calculate what is our upper control limit, lower control limit for X bar chart, and also upper control limit, lower control limit for the R chart. So this is how we calculate those. Should be pretty straightforward. And also then we can draw the X bar chart because we already have, right? We already have those data points. We already have those data points. We can use those data points to draw this. And remember, in each control chart, there are some of the basic elements. We need to have upper control limit, show the lower control limit, show the center, and also show each data points here connected, as well as the attribute values here, right? And our sample numbers here. So these are the basic elements of control charts. With X bar values, with the R values, then you can draw all of those charts. Okay. All right, we talk about X bar chart as well as R chart. Now let's look at another chart, which is called P chart. So P chart means we want to find out, what is the percentage, right, or probability of the defects among certain observations or among certain sample, right? So in this case, how do we calculate that? And first, we need to find out, okay, the P average values. So P bar here is calculated by with number of defective parts divided by number of observations. So for example, we observed 10 items, and then we found out only 2 are bad, right? Have the defects. Then that will be P1 will be 2 divided by 10, right? Then we can calculate some other samples, averages, and then find out that other, P1, P2, P3, P4, all of those. And then we calculate there's a SP here. So SP is the standard deviation for that, and then the way to calculate that is we use P average times 1 minus P average divided by N. N here is a sample size. Remember, N is a sample size. Okay. And then if you want to find out the upper control limit and lower control limit, we can use this equation. For example, upper control limit equals to a P bar plus Z times SP, and Z is the number of standard deviations for specific confidence, right? For specific confidence. Now let's use one example to show it. All right. So say, an insurance company wants to design a control chart to monitor whether insurance claims forms are being completed correctly. The company intends to use the chart to see if improvements in the design of the form are effective. To start the process, the company collects data on the number of incorrectly completed claim forms over the past 10 days, right? So over the past 10 days. And the insurance company processes thousands of forms each day, and due to the high cost of inspection each form, only a small representative sample was collected each day. So how many samples? 10 samples, right? And what is sample size? Now let's look at this table, and the data and analysis shown in this table. And we know we collected 10-day samples. So each sample, we have 10 samples. Each sample is, we have 300 data points, right? Because of 300 observations, right? 300 observations are inspected. All right. And the number of the incorrectly claimed forms within the 300 is, each day is different, the 10, 8, 9, 13, 7, blah, 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 blah. And then in this case, we can do what? We can calculate the P1, right? P1 is the probability of defect parts, right? Or defects. And P1 equals to 10 divided by 300. P2 equal to 8 divided by 300. P3 equals to 9 divided by 300 until P10, right? Equals to this. And then we have this P1, 2, 3, 4, 5, 7, 9, 10. Then we can calculate what is the P average, right? P average. P average. And all, you can use, add it up all together, divided by number totally inspected, it's the same, right? You can also calculate this. And then the next time we calculate the standard deviation, sample standard deviation, you can use this equation to calculate, right? We have the P bar, we know the sample size, which is 300, right? Then we can calculate the SP value. And in the end, we're going to use the equation we have here. Oops. Right, to calculate the upper control limit and also lower control limit. So here, upper control limit equals to P plus 3 times SP. All right. Why is we are using 3? Right? Why we are using 3? It's because 3 is the Z value here. Z value here. And what we want to achieve is, if we want to achieve about 99.7% confidence, right? 99.7% confidence means what? 99.7% that we are all good, right? All the parts are good. We are that kind of confident. Then the Z value will be 3. Remember, when we are using a normal distribution to show the variations, right? We are looking, we are at here, right? This is 99.7. Okay. Pin this. Why cannot change? Pointer, pin. I don't know why I cannot change this back to pin here. All right, back pin. This is 99.7%. Now remember, we're talking about normal distribution. How do you find out the VZ value, right? We know the percentage. Then we can go to the table and then find out the Z value here is actually 3. Then you find out the upper control limit and also lower control limit from these equations. And after we have our upper control limit, lower control limit, then and also all these, P1, P2, P10, then we can actually draw a P chart, right? We know this is the lower control limit. This is the upper control limit, and these are the P points. So this is how we draw a P chart, right? Now we talk about 3 different charts: X bar chart, the R chart, as well as P chart. All right. So how do we interpret all these charts? Sometimes it's not always that, as long as the the values are within the range, means everything is okay. It's not the case, because something we can certainly tell there's something gonna be wrong, right? For example, a more normal behavior will be like this. You will see there's no apparent, or clear pattern. It's more of a random. You cannot predict where, the next point is gonna be, right? So this is the more of a normal behavior. Well, sometimes you will see, a point is outside the control limit means there's something wrong, right? It means something wrong with the process. And also sometimes you will see there are two points actually pretty close to the upper control, and I'm gonna cause on the poor performance. Usually in this case, it also gonna indicates that there's something wrong with the process. Maybe later we'll keep tracking it, it will actually have points that is outside the limit. So from here, you might want to be aware that you need to investigate or pay more attention to this process and see what's going to happen, or trying to diagnose if there's anything wrong with the process itself. And same here, right? If you see some 2 points are pretty close to the lower control limit, that also means there might be something wrong. And another thing is, if you see a series of points that is all above the central line, means there also may be a shift of the center, or maybe something went wrong that will actually keep increasing the value of the data points, and eventually it might go outside the control limit. So you'll be start to investigate what's going on when you see those patterns similar here, or sometimes you'll see this kind of more of a cycle way of up and down is also not very normal, right? This erratic ones also you need to pay up more attention, and this kind of a sudden change in level is also worth investigation. So this means that in control charts, you can actually use those charts to help you look at if there is more visualized look at if there's something wrong going wrong right now with the process, that maybe the value you provided is still within the control limit, but you can predict, you can see something actually went wrong in the process itself. All right. Next, I want to talk a little bit about the different quality control programs people are using in manufacturing companies. One is the total quality management, another one is the Six Sigma, and also ISO 9000, 1900. So total quality management means it's actually started from from the time after Japanese started to dominate the quality in automobiles and also those durable goods. And after Second World War, Japan really survived and also revived their production, and by making really good quality products. And to react to that, American manufacturing companies start to pay more attention to the quality, and this is how people started this total quality management. I suggest you watch this video and look at in total quality management what is actually involved. So basically, it means that not the quality itself is not just the operators right responsibility, who is working on the last process on really touching the products. Now the quality actually starts from every employee in the company, from the top management to the shop floor operators. Everyone should be responsible for the quality, and also should develop policies on how to analyze, how to maintain all of those. And so this is a total quality management. Another one is Six Sigma. So Six Sigma actually have two different meanings. So one is Six Sigma is a program that people use that to achieve higher quality, which means that Six Sigma mean, if you look at this normal distribution, right? This is the 1 sigma, 2 sigma, 3 sigma, 4 sigma, 5 sigma, 6 sigma. So when you achieve 6 sigma, actually the probability of getting the poor defect is actually very, 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 very low. In this case, this is called 6 sigma. And later it actually became a program that more continuous improvement are also use statistical analysis to improve the quality. So this is Six Sigma, and Six Sigma is also can also mean program for solving problems. So which means that is define, measure, define, measure, analyze, improve, control. The make process. The make process is the way that you to guide you through how do you define a problem, how do you find out how to measure the problem's performance attribute, right? And also how do you analyze? They give you a set of two different tools to help you to analyze the problem, finding the root cause, and also they come out with a solution and to improve the problem, improve the system or the process, and then you control it, right, to sustain its performance. So this is Six Sigma as a program for problem solving. And lastly, another widely used program is ISO 19000. So ISO 19000 it has been used a lot by manufacturers to. So basically, this is to show that the company has prepared documentations or the policies on how do you control the quality issues, how do you control the quality of your products, right? And if you have all these policies implemented, prepared, and then all the measures, everyone understand what you do, then you can get this certification, and then when your customers or when your suppliers, or something like that, people we are working with know that you have this certification, then they will trust you have better quality in your production products. So this is about ISO 19000. But a lot of times ISO 19000 it only gives you very kind of a minimum requirements, and company usually develop their own quality standards that is much higher than those. Right. So these are the different widely used programs about quality control. All right, so that's all about this lecture.